In this video, I want to do a few quick examples of how to find the answer regarding a problem involving normal distributions using the empirical rule, or 68, 95, 99.7 rule. Now, in my very first attempt at this, I'm going to actually sketch the normal curve, but to save time for you guys, when I would do my next couple, I'll have the normal curve pre-sketched. But I want to draw this out, and I want you to watch me draw this out because this is the procedure that I'd like you to use. Now, you won't have to use this forever, and you won't be drawing a million of these, but I would like you to get some practice in drawing these normal curves as I'm about to demonstrate. So first of all, we have this problem. It says a machine fills a 12-ounce potato chip. A machine fills a 12-ounce potato chip bag or bags. It places chips in the bags, but not all the bags weigh exactly 12 ounces. This is pretty real world, guys. The weight of the chips placed is normally distributed because that's what happens. Sometimes you'll get a little more than 12. Sometimes you'll get a little less. But very rarely are you going to get very little, and you're not going to get like 1 ounces. And very rarely are you going to get like 24 ounces. Okay, so that's why normal distribution is probably a good representation for this problem. All right, so they tell us the mean is about 12.4 ounces, and they tell us the standard deviation is about 0.2 ounces. So they then ask the question, we have been asked to determine the following probabilities to aid in consumer relations. Hey, this is real world, people. You might have a company that makes stuff, and there might be some variation in whatever it is that you produce. So how can you make sure that consumers are generally happy, or at least they feel well informed? Well, we start with A. If you purchase a bag filled by this dispenser, what's the likelihood it has less than 12 ounces? Well, let's take a look. Let's draw the normal curve. So if we believe that the potato chips that we get out of this machine, if we believe that the weight of the bags is normally distributed, let's go ahead and I'm going to go ahead and put my x-axis down, and then I'll put the line where I believe my mean is. So I'm going to go ahead and designate the mean with the Greek letter mu. And that's because the normal model itself is a model. It's not a sample, and it's really not even a population. We use it to model what we believe would be true of the underlying population. Okay, now we're going to mark off 1 standard deviation, and then 2 standard deviations, and then 3 standard deviations, and we'll do the same thing over here. -1 standard deviations, -2, -3. And just for the heck of it, maybe I'll go ahead and put the numbers here, and I'd like you to, oh, wait a second. The numbers won't be 1 and 2. We already were told the mean is 12.4. So I'm going to go ahead and put the mean is 12.4. And since we know that the standard deviation is 0.2, we'll put 12.6. And if we add 2 more to that, we'll put 12.8. And then that last one will be 13. Okay, great. And sorry that is so messy. We'll make them cleaner on the other side. So if we do less 0.2 from that, we'll do 12.2. And then we'll do the other one will be just 12. And then the other one will be like 11.8. So if we go 3 standard deviations below the mean, we'll be at 11.8 ounces. Okay, now I'm going to go up 1, 2, 3, 4, 5, 6, and that's just kind of a rule of thumb. You can do whatever is comfortable for you, but I'm definitely going to put my inflection point at 1 standard deviation, and I'm going to go down a couple from the 6 to do that. I'll go down a couple squares from the 6. Now I'm going to go ahead and draw a concave. And then we'll draw another concave, something like that. And then we'll draw a convex that swoops down so that we're just about at the x-axis as we go over the 3 standard deviation mark. And I'll do the same thing over here. Yay. And now I can begin to use this drawing to do my calculations. The next part is something that I would like you to do for all your drawings from now on regarding normal distributions, is I would like you to really clearly mark, the book calls them cut points. In this case, we're concerned about what is the likelihood that a bag has less than 12 ounces. Well, here's 12 ounces. So I'm going to go ahead and use a red line. And again, this is what the book uses. So I'd like, it'd be great if you could as well. And we're going to call that a cut point. That's a cut point. And I'm not entirely, I guess it's because that's where we're slicing through the diagram. The other thing about it is that happens to be the x value, but by the way, in this case, x equals 12. Okay, that's our x value. Um, for that particular line. And what we want to know is we want to know what's the probability that we end up getting less than that. So we're going to shade, and I'm going to use green just because it's convenient here, to shade what part I'm interested in. So I am hopeful. And by the way, if you, I hope you're with me on how practical a calculation this is for this particular problem. Imagine that you're selling a product and you advertise on the package that it's going to be 12 ounces, and people start buying it, and they're buying and buying and buying and buying, and they're getting less than what's advertised on the bag regularly. That would not be a good thing. So in our particular case, what we're going to do is we'd like to find out, well, what is the probability that they would get less than 12 ounces if we were shooting for 12.4. Okay, in other words, we're trying to be generous because we want to make sure that even though we know there's variation, that most people are not going to get ripped off. So let's take a look and see what the percent is going to be over here. We know from the 95, 90, let's go ahead and say the 68, 95, 99.7 rule. So 68% is going to be one standard deviation. We know that if we go out two standard deviations, we're going to go to 95%. So we have to go out two standard deviations for that. We'll go in both directions. And I kind of feel like I just feel like a little OCD here. Sorry, guys. Let me get rid of that. You could still have cut point in your notes. It wouldn't hurt a thing. Okay, and we're going to say that's 95% of all our data. Now, something else that's really important to note here is that if we look at the entire bell curve, it should represent 100%, but you have to go really far to the right and really far to the left in order to get to 100%. But one thing that we can say for sure is that if this area is 95% and the rest of it is 100%, then if we go all the way from here to the left, and if we also go from here all the way to the right, those should add up to 5%, because 95 plus this should equal 100, okay? And so therefore this part plus the part over here should be 5%. Well, if this part and this part are 5%, then each part should be 2.5%. And that's how I'd like you guys to figure it out. I know that we've already seen that you can have like 2.35 and 0.15. That's ridiculous to try to memorize that, in my estimation. Let me go ahead and also let's label the green. What we're saying is the green shaded area should be 2.5%. Okay. Now, for the first time, we have a really practical situation, so we should really understand what that 25% means. I'm sorry, the 2.5%. What it means is that if we shoot for a mean of 12.4 ounces when we sell these potato chips, what'll happen is about 2.5% of the time, somebody will get less than what they actually deserved. In other words, most of the time, 97.5% of the time, our customers will get more than what they bargained for. Now, there's a whole nother discussion about, is that 2.5% tolerable, and what could you do? You know, what are the reasons that we would consider that to be acceptable in a business context? But for right, we'll have that discussion amongst ourselves. I don't want to do that in video. So anyways, so I'm going to leave you at that. There's my first example. The next ones are going to go much quicker because I'm going to have the normal curve pre-drawn for you. So now I showed you how to properly draw a normal curve and with shading when working on a normal calculation problem. And I will tell you that I consider the picture with the shading part of the answer. So if you don't include that, then you can't get credit for giving me an answer. So keep that in mind, please. Let me show you another example. In that case, we had a particular x value, 12, and we drew a cut point, and then we said what would be the percent of potato chip bags below that, or the percent of customers that would get a potato chip bag for less than 12. Now let's take a look and see if we have to go more than some value. Now, in this particular case, in the canned question, it says more than 12. I don't want to do more than 12 because that's going to be too boring. I'm going to put the cut line at the cut point at the same place I just did a minute ago. And then we know that if you go 2.5% to the left, you're going to have to go 97.5% to the right. So it's less interesting of an example. So just for the heck of it, now I don't have a great reason for it other than because I want a different I want a different cut point for you. We're going to go ahead and say we'd like to know what is the probability that they get more than 12.6 ounces. Now, do I have a great reason as to why I want to know that? No, just because I think it's going to make it a better example for you. So anyways, I'm going to go ahead and I'm going to draw my red line, which is my cut point, all the way through the 12.6 mark. And we can use the empirical rule because it is one standard deviation above the mean. As long as we have exact increments of one standard deviation or two or three, we can use the empirical rule, the 68, 95, 99.7 rule. Now, with the empirical rule, what we know is that the middle from one standard deviation away in either direction, the middle part is going to be 68% of all of our data. And because we know that if we looked at all the data that goes to the right and all the data that goes to the left outside of that middle 68%, it must add up to 32%. And if it must add up to 32%, then half of 32 must be here and half of 32 must be there. So we're going to go ahead and say that this part must be 16%. Okay, and that's the kind of logic and reasoning I want you to use when you're using the 68, 95, 99.7 rule. Now, there are other ways to do it. You can look up all the decimals for this section and this section and this section, 2.315, 0.15, whatever that one is, 13.5. Ridiculous. Just remember 68, 95, 99.7, okay? That's the best way to do this. And again, some other things that are helpful here is that the whole curve is 100% and half of it is always going to be 50. So you can use that also. But there's no good reason to memorize 2.35%. The highest probability is you'll memorize it incorrectly. Now, let's go ahead and do some shading because I am telling you that a diagram, a normal curve picture is required. Make a picture, rule number 1, 2, and 3. And the picture should have the shading that represents the context of the problem. So in this case, we're going to shade everywhere above 12.6. And that'll be and by the way, this helps us to do a sanity check on whether our answer is correct. So sometimes when we're doing normal calculations, we get it backwards and we put the high percent instead of the low percent. But if we can see this much is shaded, I can see this is not the majority of my diagram, so it must be less than 50%. In this case, we've already said that because of the 68, 95, 99.7 rule, the shaded area must be 16% of the data. Okay. That is the amount of data that is more than one standard deviation above the mean. All right, we're going to do one more example where we look at the use of the empirical rule for when we're in between two cut points. So let's take a quick look at that. In this last example, we're going to try to calculate what percent of potato chip bags are between 12.2 and 12.8 ounces, given all the same information that we've been using. I've pre-drawn the normal curve, I've drawn all the x values. Sadly, I'm going to ask that you guys do this drawing for each problem. I just won't give you a million problems. Anyways, notice also that I've pre-drawn the cut line at 12.2 and the other cut point at 12.8, and I used red to indicate those cut points. I guess when you get cut, you're going to bleed. Maybe that's why I use red. Anyways, so how do we figure out the percent in between these two using the empirical rule or the 68, 95, 99.7 rule? Well, we know if we go one standard deviation from the mean, we got 68% of the data. If we cut that in two, then this part right here must be 34% of the data going from here to here. This must be 34% based on the 68, 95, 99.7 rule. Now, we also know that this part over here must be 34%, but that doesn't help us to figure out this part here. Now, I know that you already saw in a picture what percent this is, but we're going to figure, I want you guys to have a way to derive it from 68, 95, and 99.7. So, if we go all the way from, if we go all the way 2 standard deviations from the mean to the left, and all the way out to the right, same thing. That's 95% of our data, according to the 68, 95, 99.7 rule. Okay. Now, if that's the case, then this part right here must be half of 95. So what we're going to do is we're going to go 95 divided by 2, and whatever that happens to equal, I think it's something like 45 and 45 is 90. So I think it's like 47 and 47, but with halves. So 47.5, I believe. Later on, I'm going to be really embarrassed if I'm off, but I think that's 47.5%. So what I'm going to say is because of this, this must be 47.5% from the mean, not the median, from the mean all the way over to 2 standard deviations, which is where 12.8 is. Now again, all of these examples I've been giving you today are only useful if we have exact increments of 1 standard deviation or 2 or 3. We'll learn some ways to do this when we have fractions of a standard deviation. So anyways, then we just go ahead and add 47.5 plus 34, and the answer will be whatever that is. I believe that if we add 34 plus 47.5, I believe we get 81.5%. And since that is our answer, I will go ahead and box it. And again, let's really take it all the way back. The question we're trying to answer is what percent of potato chip bags are between 12.2 and 12.8 ounces, given all that other information that we received before? And the answer is it must be about 81.5%. Now, one of the things I'd like to point out to you guys is that for some of us who are new to the normal curve, this is going to feel a bit odd that so much of the data could be there when there's still it looks like there's so much area to the right and to the left. And the problem is it's just that I'm not very good at drawing my normal curve. These guys should probably sneak down a lot faster than the way that I've drawn it. So anyways, I will leave this is it. That we finished this example. Now I'm going to give you some practice problems and you guys are going to try. Remember, you're going to draw the picture, you're going to draw the cut points, you're going to label the x-axis, and you're going to shade the, oh, I didn't shade the area of interest. I'm being a hypocrite here. Let me go ahead and use green to shade my area of interest. And I'm just going to cover up those numbers. You have them from before. But this is what I'd like to see you guys do. And if you have to put numbers in there, you could just do something like, well, this is 47.5, and then this part over here is 34, and that will let me know that you know what you are doing. All right, folks, that's it. Let's crunch some numbers. Let's try some problems ourselves.